Hey everyone, welcome back to my channel. In today's video, I'm going to discuss how we linearize a non-linear function around the steady state. This is a technique which we are going to use throughout this semester, so I thought it required or basically deserved a video on its own. Okay, so before I start to explain what linearization is, let's discuss some terminology. Remember that capital letters, let's suppose it's capital MT, that denotes money supply in aggregate levels. So this is an aggregate level of a variable. Whereas a small mt is the log of the capital variable. And so how do we, what's the growth rate of a waste? So for example, if I say the growth rate of money supply, it's the change in money supply, right? And since this is a small number, remember the linear approximation of ln 1 plus x, when x is a very small number, it's approximately equals to an x. So since this is like in a 0.15 whatever, it's a percent, so it's a small number, I can write it like ln 1 plus a ratio. Okay. When we open this ratio up and make the common denominator, I'll be left with mt over n mt minus 1. Therefore, whenever you see log mt minus log mt minus 1, you just understand automatically that that is the growth rate of that variable. Similarly, there's another variable variable called m hat t. That is just the deviation of money supply from the steady state. And we do the same mathematics here because this is a small number. We can write it as a 1 plus the small number. And when we simplify this, there's an approximate sign here actually. This will become a log of mt over m bar. And this then is written as ln mt minus ln m bar. So whenever there is a hat variable, so I say x hat t, it's just the log of that variable minus log of the steady state value of that variable. Okay, and remember these log deviations are identities, are exact identities, which means that you don't really need to do a Taylor expansion. For instance, if I did bother to do a Taylor expansion, I would have written there's a function f dependence upon m, and that is log of, okay, ln log of mt over m bar, right? So if I start taking, let's just open this up. This is a log mt minus log m bar. So if I take the tail, this is a constant, so the only variable that will require linearization would be this. And as you can see, the linearized version, so a log mt is just going to be a log, the value of function at the steady state, plus the derivative, which is 1 over mt, and at when m takes value m bar, so it's just going to be m bar. And then we have a mt minus m bar, the deviation, right? and therefore we just get a log mt minus log m bar is equals to 1 over m bar of mt which is we just defined this as the deviation of m, any variable, from the steady state. So on the right hand side we have the variable x hat t. So this is circular logic. There's like no point in us doing the linearizing a function which is in logs. Okay, so let's do a question. Suppose you get this question. You get a question which is asking you to linearize this function. So it's mt over pt is equals to ct. Ct is consumption and some function of the interest rate. Okay, so one way you can do this is, let's just call it method 1. We take the logs on both sides. So we have log mt minus log pt, and we have a log ct plus a log fit. And then from here we can use the identity, which is that when we have any variable x hat t, it is the same as log of xt minus log of the steady state value. So therefore, if I want log of the variable, that is just the hat of the variable plus log x bar. So I can use this identity at 3 places: over here, and over here. Okay, so therefore we end up with an m hat t plus log m bar, right, minus p hat t plus log p bar, and c hat t plus log c bar. And this right here, because f is not known, and most probably it's actually not linear like this, so it's going to be a non-linear mapping, so we'll have to do the Taylor expansion separately for this. Okay, so let's first write out this equation in terms of like this. So ct on the right side, and let's put all these constants together. I'll have a log m bar, actually that becomes negative, so this is log c bar plus log p bar minus log m bar plus log fit. Okay, and in the steady state, remember, in the steady state, all variables, so like mt is at its steady value, state value, pt is at its steady state value, consumption is at its steady state value. Therefore, there is no deviation from the steady state. Therefore, m hat is t is equals to 0, p hat t is equals to a 0, c hat t is equals to a 0. Okay, so if I rewrite this equation and see the equation, how it behaves on the steady state, there's just going to be a 0 here, 0 here. All these constants will remain the same, and we'll have a log and this function at I on its steady state. If I deduct this equation from the above one, remember signs will reverse, so this becomes a negative, this becomes a negative. All these constant values will disappear, and we'll be left with m hat t minus p hat t is equals to c hat t plus log f I t minus log fi bar. Okay, so this is what we get, and now we have to, on the final step, we have to find the Taylor expansion of this. So because this is, remember, we need linearization. Let me just write it down. We need linearization for non-linear mappings. Okay, so let's do the Taylor expansion. Remember, when we have a function fx, then we around and want to see the behavior around x bar, it's going to be like this. The first derivative at x bar and x minus x bar. Okay, this is the first order Taylor expansion. Okay, so in this case, we'll have a log of fit. The value of this function at the steady state is just I taking on the value I bar. The derivative is 1 over fit, and the derivative of fit in the numerator, and we evaluate this at the steady state, so it is equals to I bar, and then we have an it minus I bar. Okay, so therefore we wanted to find the answer for this, actually, this whole thing. So if I take log fi bar on the other side, we'll have an equals to sign there and a minus sign here. So let's just substitute that. What will be our linearized version of the function? We'll have this here plus this here. Okay, sounds good. And at this point, you can state that ki, which is just the elasticity, is equals to this number, whatever it becomes when the function is given. It's usually negative. And you can call the deviation of the interest rate from its, it's not log, so therefore I'm not using the hat, because then we'll just become confused. Therefore I've not used the hat, I've just made the symbol here, plus ki and I bar. Okay, so like the only thing like I find objectionable about this method, this is like the formal pedagogical, like this is the method that will work on any kind of equation which is non-linear, right? But I somehow find it quite tiresome. So I solved it another way, and I did ask ChatGPT if I'm correct or not, and it did tell me that I am correct. However, I'll tell you guys about what I thought should be a better way of solving such a question, but it's up to you whether you want to do it this way or not. I do personally feel that this is better in a way that it's more efficient. So I thought that why not just put the logs, right? So if I take logs on both sides, I end up with this, right? And why not just evaluate this equation on the steady state? So if I write log m bar minus log p bar and log c bar plus log fit bar, and I subtract the second from the first, so this becomes a negative, positive, negative, positive, then we have a log mt minus a log m bar, which we know is m hat, right? And then we have a minus log pt minus log p bar. Then we have a log ct minus log c bar. And lastly, we have, let me make sure it fits in one page. We have a log fi minus log fi bar. So as you can see, we do like end up with the same solution. So I don't understand what the problem would be with this method. It gives us the same equation which we had last time. So we end up with this, and then again we do the Taylor expansion here, and we will end up with the same result. So we will end up with the same result. So I don't know, I find method 2 slightly easier on the eyes, but ChatGPT said that method 1 is foolproof, and that's the proper way of solving such a question. But method 2 also works for a lot of functions as well. Okay, let's do another practice. Suppose they've given you the following function to linearize. They say mt is equals to pt is equals to c alpha t e minus n I t. So let's do this method 2, using method 2. So we'll have a log mt minus a log pt, alpha log ct minus n it log e. Okay, then at the steady state, all of this becomes bar values. Okay, and then when we subtract the second from the first, we subtract it, we'll get m hat t over here minus p hat t over there. Alpha can be taken out as common, and we'll have c hat t there. And then we can take minus n log e as common, and this becomes I t minus I bar, and we can call that that's not the log deviation, so let's use another symbol. Let's call it I t whatever, this sign. So like I think like this is way faster than the other method, but you will like, if you want, like I can solve it the other way as well. It actually it does give the same solution. Let me think of another question. Yeah, a lot of times in when we're doing Linear, and we're doing solo on Linear, and suppose we get a production function like this k power alpha, and we know that this is non-linear, and in order for the software to work properly, we need to linearize it. So let's do that by method 2. Log yt would be alpha log kt, and around the steady state, y is equals to y bar, k is equals to k bar. Let's subtract the second from the first. We have a log yt minus a log y bar is equals to alpha log k t minus log k bar, and therefore this is a y, sorry, hat t is equals to alpha and k hat t. So that's the linearized version of the production function. So that's it for today. This is the technique, linearization technique, which we will use throughout the syllabus. Oh, and by the way, if we had taken log to the base e, then log e to the base e is just basically 1. So ln, because we know ln e is equals to 1, so this would have disappeared because this just equals to a positive 1. So that's enough for today. I hope this lecture was beneficial, and I will see you in the next one. Take care.